Good afternoon. Today is the due of our team list. So I would like to know, is there anybody belongs to a team? Do you have a team member already? Is there anyone who haven't find his team member or her team member? Not yet? You? Okay. You have a team. Okay, good. So because last year there was a girl who was unable to find her team members. So I just asked who, because the maximum people of a team is five people, right? So, okay, I asked whether which team would like to accept her. Okay. So now if everybody has a team, that's fine. Okay. Just I want to confirm that. Is it correct? Everybody all have belong to a team? Okay, good. Okay, if so, then please let me know. Okay, please let me know. So, uh, who is your team member? So, could every team send me a message, okay, to let me know your team members or the list of your team? All right. Okay. Uh, Message or email. Either way is fine. Okay. Okay, so now we are going to talk about chapter 4 of our textbook. The topic of chapter 4 is model fitting and optimization. Why we need to, I should say, why the authors created such a chapter? Because some computer vision problems belong to this category. And what does it mean? If we have some data and it is incomplete as our input, then we need to assume there is a model and try to seek and optimize the output based on the model. Okay, so this is a concept, and there are many examples in this chapter. Okay, so first of all, what is model fitting? And the authors gives us an example. It is a scatter data interpolation. Okay, so what does this mean? It's just like this figure. Say if we have some x and d, it means it's input and output like this one. This is a simple example. The x is is a value between 0 and 1, and the d is also a value between in the as a height of those blue points. Okay, so what we want to do is we want to find a function which it can generate such a result. Given an xk, then we will have its xd value. Or okay, so you see here, for every blue point here, the function is the red curve, and it go across every blue point in this figure. And there's an alternative way to solve the problem. It's called approximated function. It means we do not ask the curve will go through exactly those blue points, but we want to let it go through approximate those regions of the blue points. But however, we need to define an error function. Usually, it is a squared term. So it is fx minus dx, and it is squared. Okay. So why the authors need to mention about this model? Because let's see this example. If we have an image, usually though every pixel on the image, they are regularly gridded. And in our last week's lecture, we show some interpolation method. Nearest linear cubic for 1 dimension, or for 2 dimension, bilinear by cubic, etc. But however, for this case, Okay, if say for this case, for every circle here, that is one of your data points. And how do you interpolate those points to the whole image? Okay, this is the first example. And another example is if you have some data points for this point, okay, and how do you generate an image from those scattered data points? Okay, so this is the scattered data interpolation problem. Okay. Okay, so for the case A, there is a solution called the Delaunay triangulation. Okay, and for the second one, there is a solution called the pull-push algorithm. So let's see what is the Delaunay triangulation. Okay, so the problem is given a set of points, we know its location and its value. Then we can create a mesh. There are several possible. For this is one. We create many triangles to connect those points. But however, they are not unique. So for case 1 and case 2, there are two possible cases. And the Delaunay triangulation, it has a property. It means, okay, so this example, the rule is no vertex lies inside the circle of any triangle. Okay, so let me show what does it mean. Given a triangle, for example, this one, this is triangle. Then what is circle? Its circle is this. Okay. So is there any vertex or any point in the second circle? No. Okay. So, but however, if let's see this point, okay, for this triangle, okay, if I create a circle, it will like this. It will be a very large circle like this one. For example, okay, then you will see there are many points here, 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 and here, and this. Okay, all of them are inside the second circle. So therefore, this is not a Delaunay triangulation. So what is the meaning of Delaunay triangulation? It will avoid very thin, very narrow triangle in the set of data. And what is the benefit of the Delaunay triangulation? Well, if you can create many triangles, they are very, well shaped. Then, in the graphic problem, if you only have data on those points, okay, it will relatively easy to use some interpolation method to generate values in this region. Therefore, for computer, it can use the mesh and those input data to create graphic images. Okay, so once we know the definition of the Delaunay triangulation, the next problem is we will ask how to create the Delaunay triangulation. Okay, and here I show an example. The widely used Bower-Watson algorithm. Okay, so let's show an easy example. Suppose we have point and we want to create a Delaunay triangulation. The first step is let's create a virtual large super triangle like this one. Okay, it will enclose every given point. Okay, then we create its second circle, this one. Of course, because it will cover those input data, so this is not a Delaunay triangulation. Okay, so next, let's pick any point in the input data. For example, this one, I use a different color to distinguish it. Okay, then let's connect this point to its super triangle. Okay, then okay, for those points, we can create some second circle. So this one and this one. Okay, then we can find, okay, they have some common edge. This is the common edge. Therefore, we remove this common edge. And okay. Oh, sorry. Let me start from here. We created this. Okay, from this point, we created a new lines here. Okay, and then here we check another. We pick another point to check. Okay, here this time we check. We pick this point, and then we check which triangle. So see, now we have 3 triangles, and we check which triangle's second circle will cover this point. And we found the 2 second circles, this one and this one, it will cover this point. Then is there any edge commonly shared by the 2 second circles? Yes, this edge. Therefore, we remove this edge. Okay, remove and check the point connected to those triangles vertices. So we will connect this line, this line, this line, and this line. So it will become this new triangulation. Okay, and now we check this vertex and this vertex already. Okay, so there are 2 vertices remained. Next, we check the 2 vertices. Like we just pick one of them. Then this one, say this one, and then we check again. For those triangles, both second circles will cover this point, and we found yes, there are 2 triangles. First one is this triangle, okay, and the second one is this triangle. They will cover, their second circle will cover this point. Then again, we remove their shared edge, okay, and then connect this point to those triangles vertices, this one, and this one. Therefore, we got this new triangulation. Okay. Then again, there are 1 vertex remained. This is a last second vertex. Again, we check which triangle second circle will cover this point, and we found there's only one. It's this triangle. Okay, and then is this, so because it is a single triangle, there is no common shared edge, so we don't need to remove any edge here. We just connect this vertex to the triangle's vertices. Okay, then we create this triangulation. And finally, we remove the virtual super triangles 3 points and all connected edges. This one, this one, this one, and this one. Every edge is connected to the super. Okay, therefore, after removing those edges, we will get the Delaunay triangulation. So this is an example to do it. Okay, so let's go back to another question for this one. How do you generate values? For example, say this, okay, from those scattered points. So let's see the pull-push algorithm. The idea is, okay, let me show the algorithm in a one-dimensional example. Say, okay, there is some cell which contains a value, say x2, 0, x, say this, and this. Okay, the approach of this algorithm is it will create a pyramid, okay, like this one. In the bottom, the resolution is highest, and the resolution is slightly reduced, and finally it will reduce to a very, very small single cell, like this one. Okay, so this is a single cell. Then, so what it do is use some equation or formula to copy the value in the high resolution cell to its next layer. So we copy here values from here to here, here to here, and here to here. If both cells have the value, so there is a certain weighted average from this to here. So finally, okay, you will feel some cells in the image pyramid. So this is the pull phase. And then there is a push phase. For example, the x01, it is empty in the beginning. But however, we know its parent cell's value. So we copy the values from its parent to its child. And then we copy the values from this child to this child again. Therefore, we can fill every cells in the image pyramid. So let's see an example. Okay, say if we have values here and here, and here, those vertical bars is the given value. Then use the pull and push algorithm. We will generate a result as the solid line. This one. After the first point, all of the value will be the same as the first point. And the dashed line means if we use another set of coefficients, we may generate a result like this one. Okay, now this is a one-dimensional example. How about the real image? So let's see this example. So this is Lena. It's a very famous benchmark image for computer vision. Okay, it means if we just remove most pixels and remain those pixels, then after applying the pull-push algorithm, we will generate images like this one. So what does it mean? Say for this region, we have no input value, but there are some input data here. Therefore, according to the pull-push algorithm, the values of this region will be copied and extended to its neighboring regions. Okay. So this is a result of the pull-push algorithm. Okay. All right. So why do we need? So you currently see two examples. The common properties, you have limited input data, and for many for other regions, okay. Okay, for these regions and these regions, you have no input data. And you need to find a method to interpret the given data to the empty spaces. So this is what the authors call scattered data interpolation. Okay, now we are talking. Okay, another issue. So currently, the two examples you saw was all of them are 2D dimensions. But however, how do you do for the high dimensional data? Okay, the author gives us an example. It's called kernel regression, and the formulation is like this one. The fx is the output function, and wk is the weight. Okay, and phi is a radial basis kernel, and the xk is the given input data. So it will generate result something like a linear combination. And here, what is the meaning of the radial basis data? And why it is called kernel regression? Because a radial basis function, its nickname is kernel. Therefore, such a kernel regression using radial basis functions is called kernel regression. And why is it called radial? Okay, radial because if you see this equation, you will see this is the absolute value of 2 points, x and xk. And what does it mean? It means this function only care about the radius or the distance from one point to another point. So radius, the concept of radius in two-dimensional space, it is the distance from the original point to a certain point P. And in a three-dimensional space, the set, it is the original point to another point. Okay. Therefore, there are some widely used radial basis function. The Gaussian, it is written in this format. Why it is called Gaussian? Because there is a Gaussian distribution. Okay, the Gaussian distribution. Okay, the shape of the Gaussian distribution for dimensional is look like this. It is a bell shape, and the equation for the probability density function is like this. So see here, this is the squared term, and with a negative exponential power. It's like this one. This is a square term and a negative exponential to the power. Therefore, it is called a Gaussian kernel function. And there are some other kernel functions. Usually, Gaussian is mostly widely used. All right? Yes, please.
What does the letter C stands for in those formulas? Constant?
Yeah, the concept is here. What you see here. The absolute value means the distance between the 2 points, x and k. Okay? Therefore, if we see a two-dimensional space, say if this is xk and this is x, then the radius in the two-dimensional space is just the same as the distance in this equation.
Yeah, I see, but for example, for Gaussian, there is exponential of minus pi squared divided by c squared.
Yes.
And what is c?
Oh, c is a constant. You're welcome. All right. So what is this? Let me show you an example. Okay, here. For a small c, the regressed curve will like this one. And if we enlarge the very constant c, then it will become this curve. And we still enlarge it, then this will be another curve. So C is the constant we can adjust. Okay, so in this example, we can deal with any kind of high-dimensional input data because we can easily compute the distance between two data points, no matter how many dimensions space they belong to. And let me show you an example of high-dimensional data. So this is called the Boston housing dataset. You can find the dataset from Google or from some machine learning package, some sklearn or scipy. Okay. And there are 14 dimensionals. Okay, each one has its own meaning, and the total number of instances is 506. And the first feature is per capita crime rate by town. And so you can see something like this one. 0 means proportion of residential land room for lots over 25,000 square feet. All right. So among the 14 features, the most interesting one, usually the most, I should say, usually researchers want to learn a function from the first 13 features to predict the 14th feature. And the 14th feature is the house price. So this is a house price data set. Given some feature, you want to predict this house price. But however, the data set has an ethical problem because the researchers who compose this dataset create a feature called B. Okay, the B is defined as 1,000 times of the BK minus a constant and its square, and then the BK is the proportional. Okay, let me enlarge it. BK is the proportion of black by town. Okay, so this is the problem is the author, the researcher of this dataset, it assumed there is first of all, this feature is non-invertible because there is a square term. Okay, and the second, it assumes the racial self-segregation has a positive impact on the house prices. Therefore, the Boston housing dataset has been removed from a very, very popular machine learning package called sklearn. In the first version, yes, you can easily use a function called load Boston to get the dataset. But after the version 1.0, you cannot. However, we still can use Kaggle to download this dataset. And let's take a look of the value of the dataset. So you see, if I just show the first 5 instances of this dataset, okay, so you can see those values. And the price is the last one, MEDV, median value. Right? Okay. And if I use some visualization tool, say Seaborn, to draw those features, it will look nice. Each feature has its own distribution. Right. Okay. Therefore, if we use the kernel regression formula to draw or to create to compute or not 4 points. Sorry, let me see. 4.3. Sorry, I think there's something wrong. This is not 4.3. Oh yeah, this is 4.3. Okay. So if we want to create a function like this, okay, this is the kernel regression function. And what we need to do is to define the weight vector W and its every component WK. Okay, so there are actually there are many possible equations. First, if we just want to know we want to regress the house price, then for the one dimension, our output will be the house price. And all of our remaining features will be the input, is like the xk. And we will create a set of equations like this. The house price will be the summation of those kernel radial basis functions with their weights k. Or if we have the two-dimensional output, say if we want to predict two features simultaneously, then our output will be a vector, and there are two components in the vector, and our input will be the remaining 12 features, and they will become a vector like this one. Okay, the next problem, how do we solve the WK? Okay, say there are 506 equations. Let's write it another form like this. Okay, so they will price 1, price 2 to price 506, and each of them is equal to the combination, linear combination of the weight of k, because we can calculate those radial basis functions value independently. And finally, we will get the equation like this one. So this is the price vector, and there is a matrix times our weight vector. And since this is the square matrix, so we can calculate it inverse matrix. So the weight will be the inverse matrix times the price vector. Okay, so it is solvable. But however, for linear algebra, there is a case. It calls yield conditions. For this inverse matrix, it is possible that if we slightly change the price value here, then the weight value will change very, very significantly. So for the yield conditioned case, it means our system inherently it is unstable. So how to solve the problem? The problem is we regularize those weight coefficients. So that's here we add a new term. It's called the error of the weight. So very simple. Just calculate the sum of the absolute sum of the weight or the square terms of those weights. Okay. So for different cases, if we set it as a square term, then it has a net. It's called a range regression for the machine learning courses. And in the neural network community, it has another name. It's called weight decay, because the term will encourage those weights to decay to 0. And if we set the value as 1 for the p, then for the machine learning community, it has a name called lasso. But it is not the lasso. It's just a short for least absolute shrinkage and selection operator. Alright. Therefore, the overall error term would be the summation of the two terms, and here is a lambda. The lambda is a hyperparameter to balance the data term and the weight term. Okay. And if we expand the two terms, we will get this term. So this is the set, the 4.2. And this is the data 4.9. Okay. So why, okay, the question is, why is it called range regression? The reason is, this is a range. It is the shape of a mountain or something else. Okay. And if we change the value of the lambda is here, it is a hyperparameter to balance the two terms. If we slightly change it and we seek the optimized data of the weight, then it will like this one. If we use a relatively large lambda, then most of the weight will be suppressed to 0. And if we use a small lambda, okay, here, please be this is 10 to the negative 14, and this is 10 to the negative 7. So this is a relatively larger number, and this is a relatively smaller number, right? Okay. So if we slightly continuously reduce the value of lambda, then those weights, they will greatly become larger, and the shape of these coefficients looks like a range. So this is called range regression. Okay, so there is a method called kernel regression. Kernel regression is like this. Since we have some kernels or the radial basis function, then we can use them as the weight to weighted average the input data decay. And the advantage of this approach is there's no parameters. You don't need to tune anything. Okay, and it's very straightforward. Just when you decide your kernel or your radial basis function, then it's very easy to compute those weight and just sum them up. So this is example. Say those brown points are our input data. Okay, so we have their weight x and their d, right? And this is kernel. This is the Gaussian distribution for each point. And for each point, the authors use a different value to show it. Okay, so say for this point, for itself, it will be, wait a moment. It will be this distribution, right? And for this point, it will use this distribution. Okay. And for this point, it will use this distribution. So those distributions will contribute to the weight of the weighted average is like this. This is the weight decided by those kernel functions, and their weighted average, okay, will be okay. Okay, so there are some stars here, so it means their weight in the equation. And here, right? Okay, so we can calculate their weighted average as a function. So for small c means the shape of the pair will be much shaper than this one. Okay, and for large c, the shape of the Gaussian distribution will like this. It is flatter. Okay, so it means it will be averaged by more pixels or input data in this figure. So therefore, you can see it changes very significantly locally, and for large C, its change is less significant across the input region. Okay, so the kernel regression is a useful and actually convenient way to do what? Scatter data interpolation. So this is the first section of this chapter, scatter data interpolation. Okay, now we are going to talk about the second section of this chapter. It's called model fitting. Okay, so and in this section, the author Richard Selsky, used a lot of figures from this book, and this book is a very famous book for machine learning. The title of the book is Pattern Recognition and Machine Learning by the author of this book is Christopher M. Bishop. And who is he? He is the director of the Microsoft Research at Cambridge. Okay, and now you see the book is very old, 18 years ago it was published. And then now I still use this book for my machine learning course. Okay. Oh, the reason is there are a lot. I should say the book is very well written and very, to say, solid. There are numerous mathematical equations, and it explains the machine learning very clearly. But however, there are some, I should say, for example, for some students who learn machine learning, sometimes they want to learn how to use tools. But in this book, there's no Python code, no tutorial for using any, say, SciPy, stlearn, etc. This is a very theoretical book. However, this book is free available. Everybody, the author, Christopher Bishop, he offers this book as a PDF version online. Everybody can download it from his website. So, let's go back to the model fitting problem. Okay, so what is model fitting? Model fitting is I should say our Richard Selsky showed me as an example. Use Bishop's textbook. Say this, the green. Okay, the green curve. It is a function of sine. It's a sine function from 0 to 1, and use the sine of 2 pi x. We can generate such a very simple function. And if we draw some samples from this function, okay, they are those blue points. But you will see, why are they not on the curve? Because there is noise. Because of the noise, our observation value, sometimes it is greater than the sine function, and sometimes it is smaller than the sine function. Okay. Therefore, we want, based on those observation values, we want to create a model based on those points to simulate or to figure out what is the ground truth model of those data. Okay, so I should say, if we use polynomial function to fit those or to model this data, the polynomial function equation will look like this. There is a sequence of weights W0, W1 to Wn. M is the order of the polynomial. Okay, and what we need to do is to determine those weight values based on the input data and this model. Okay. So how to determine those weights? Okay. Suppose we use the sum of squares, the error function. It means if we have a model and given those x value, we can create the return the value like this one. And then there will be a distance or the error. It means the given input data and the model's predicted data, then there's error term. And we sum, so it will be written as this. The difference between the observed value and its predicted value. So we sum those error term up with a square. This is the sum of the square error function, right? Okay, so for this case, then this is a zeroth order polynomial. It means our m is 0. And let's go back to this equation. Okay. Here, so if our m is 0, then we won't have those terms. All of them are empty. We only have a single parameter, it's W0. And for this W0, okay, it will be what? It will be the mean of this t value. The t value are the height of those blue points. So it will be like this. Okay. And the error term will be the sum of those values, this, okay, this is the error terms. Okay, by minimize those error terms, we will get the weight of the W0 as certain this like this. And okay, let's see, this is a first order polynomial term. So it is a sloped line. And let's go back to the definition of the polynomial. Okay, it would be we won't have this term because m is 1. Okay, so we have two parameters. It will be W0 and W1. So that we can see it is the line, but we have a slope coefficient. And again, the error term will be the sum of this distance. Okay. Okay, see, so this will be the third order polynomial, and this is the result of ninth order polynomial. So when you see this figure, you will be something wrong. What does it mean? The curve, the red curve, it looks very unlike the original ground truth model, the sign function. So, and if we see their weight, it will look like this. For zeroth order, first order, and the third order, those coefficients looks reasonable, not very large. But for the ninth order, the coefficient looks like too large to make sense. Okay, so, but however, if we slightly change the data, say this is still a ninth order polynomial function, but we have more data points. Here we only have 10 data points, but here we have 15 data points. But okay, it looks like okay. The polynomial function somehow is close to the ground truth sign function. And if we further increase the number of points, say 100, then okay, the model looks good. Okay, so let's take a break for 10 minutes. Okay, so this is the another example. If we have more samples or data points, then the model looks okay. Okay, so this is so here. If we don't have sufficient model, and our model will generate a very very weird case. If we have sufficient or more model or more data points, then the model looks useful. And if we have more data points, okay, the model looks good. So what's the problem? I should say not the problem. So how to describe it? Okay, and let's see more example. In those previous slides, there is no regularization term. And here, if we add the regularization or penalty here, the red region. Okay, so what is this? Let's go back to this slide. Okay, so here, that is a regularization, the equation 4.9. And let's go back to here. Okay, so see, this is the equation 4.9 as the p is 2. Okay, so this is the regularized term. And then if say here, we need to the lambda is a hyperparameter. So let's see different cases. If the lambda is 0, then what does it mean? It is equivalent to the case 9 polynomial order data point as 0, 9 as lambda is 0 means there's no penalty term. Okay, so you still see the same curve. But if we use a small lambda, say exponential e to the negative 18, e to the power of negative 18, then you see the red line looks okay, not far away from the ground truth model, the psi function. However, if we enlarge the lambda to 1, so this red curve looks like it is not a straight line, but it looks like a straight line. So what is and why it happens? Let's go back to this slide again. If we use a relatively large lambda, then all coefficients will be suppressed to 0 or very small values, like this one. Oh, sorry, I forgot to do here. If we set a very small, very large lambda, then all coefficients will be suppressed to very, very small value. And the small value would be, in this case, it will like this one. The W1, W0 is very small. W1 is very small. W2 is very small. So the curve looks like a line very close to this horizontal line, and the slope is also very small. So it looks like small. Okay, so this is what the author want to talk. It's called overfitting and underfitting. So for this case, for when the m is small, say this case, and this case, you can see the data error tone is very large. So it is this case. It's for underfitted. The blue line, it means the error term of those training data, they are quite large. Okay, and if we set a large m number, it means our model become more complicated and there will be more weight we can adjust. Then for the case when the models, if we only have 10 points and the order of the polynomial is 9, it means we have 9 parameters, 10 parameters too. And the model is getting into a overfitting case. It means although we can adjust we can reduce the training error to a very, very small value. And in this case, how large is the training error? 0. The training error is 0 because how do we define the error term? The error term is this: the sum of those green lines. Okay, and in this case, because the red curve go across all of those points, so the error term for the first point is 0. For the second point is also 0, and for every point, all of them are 0. So sum of those zeros square term is still 0. So it is this case. We can generate a very, very small training error. But however, the model doesn't fit the ground truth model. So if we use another training validation set, we will generate a very high error term. Okay. So the blue line here means the training data's error term. And the red curve here means the error term of the validation set. Okay. In this case, you didn't. So then you will say, where is the validation set? I didn't see any validation set in example. Yes, because okay. So it means, suppose we have a data set called all data. Then usually we will split the data into 2 sets. One for training, called training set, and another for test, so or validation here. And there is a widely used practice called 5-fold validation. It means divide the all data into 5-fold and use 4-fold to train our parameters, and use the remaining fold as a validation to test the performance or calculate the error term from the validation set, and then switch the validation fold. In this case, it will become the second fold, and then we will compute the average of the 5 validation set. Then we will get the curve like this. Given a training set, we will generate a validation set and calculate the average of the 5 tests. Okay, so here, let's take another question. Those 10 points is just a set of sampled data. If we use another set of sampled data, then what will be our result? It will, of course, be different, right? But the questions, given an input set, we will observe a set of generated value, and it is noise. It contains some noise. Okay, so it looks like this. Given this, the red arrow is the input X. The output T may be any one of those yellow circles. So this is what? It's a probability. Because the noise, right? The original value should be here on the green curve. But because of noise, it can be any point among those yellow circles. Okay. So what we create another function called hx. it's an expectation of those t when the input data is x. So this is a distribution. There are many possible t values, and every t value has its own probability. But because this is a continuous variant, so it is a probability density. It means given a range of the t value, there is a probability. But for every point, it is just a density of probability. Okay, so the definition is the hx. It is an expectation of the conditional t value under x. And so the definition of the expectation is it is an integer of t times its probability dt. Okay, so you won't see this equation in our textbook because this equation is from Bishop's book, Bishop's 3.6 equation. Okay, but I need to mention it here because you will see this figure in our textbook. But if I don't use Bishop's equation and his book, it will be very difficult to explain what you will see here. Okay. Our textbook, the property of our textbook is it will mention something, and but however, the background knowledge, but the book doesn't mention the background knowledge and information. So I need to use Bishop's book to explain it. Okay, so let's go back here. Okay, so what I want to explain is what is the bias variance trade-off. You will see this term in our textbook. And there are some mathematical equations here. Okay, so first of all, if we define the expectation of the variable t, this is a noisy observation, all right? Then we can define the average loss. It means the loss, what is the loss? The loss is this. This example of loss, the difference of the observation value with respect to its expected value. So, and we sum them up, it will be a loss term. So in this case, okay, once we have a loss term, and what is the expected loss term? For every set of sampled data, we will have a loss. And because the set of observed value is generated from the ground truth model, then if we sample it many times, then we will have an expected loss value. So the definition of the expected loss will be there are many possible of the input vector x, and each of them may have level probability of the output observation t, and they have a joint probability density function. And for this xt pair, then we can calculate its value of our model y and its value. So we will generate a loss function. So the double integer of this term will be our expected loss. Okay. So here there are many possible ways to define the loss. And if we assume it is a squared term, it means the loss is our model's value minus the t squared. Then the average loss, just because from 1.186 it will become 1.87. I just replace the L by the yx minus t. Okay. So when will be the expected loss minimum? According to calculus, it will happen when the loss function, the derivative respect to y equals to 0. Okay, so let me show you something here. Okay, suppose I have a function look like this. Okay, then what is the minimum value? So the minimum value is here, right? Okay, so how do we get where is the minimum value? So suppose I have this function and I get its derivative function. And when the derivative is 0, so it will have so here this is the derivative value, and here is the derivative. The maximum value only occurs when the derivative value is 0. Okay. Any question here? This is a concept in calculus. Okay. All right. So suppose I said, never mind. Just keep it. Just get the impression. All right. So therefore, when the expected loss will be minimum, it will be if I divide its derivative with respect to y is 0. So what is the derivative of this term in respect to y? It will become, so because it is a square, so the coefficient will move here. And then it will be the y minus t times its joint probability dt. Okay. Okay, here I want to mention something about the joint probability. You might see, okay, it looks like continuous function. Why do we need to care about the joint probability? Because in some cases, here we sample the y, it looks like continuous. We don't have different density of the y. But let's see this example. Suppose this is y, this is x, okay, and this is t, right? Suppose then the x itself is not uniform. The x is either in this region or in this region. Okay, you see the probability between the two regions is relatively high than other ranges. Okay, and what is the data? This data is called old fast data set. Okay, there is a Yellowstone National Park in the USA, and the old fast geyser. Okay, well, if, some researchers records is 272 eruptions of the geyser. Okay, it will find the duration of the eruption and the minute to the next eruption, they will become this distribution. So the two variables are not evenly distributed. They found a distribution called the mixma of Gaussian. So see this, the three circles means in this region there is a Gaussian distribution, and here there is another Gaussian distribution. The joint probability is a mixture of two Gaussian distributions. So that's the reason why here we use the joint probability density function. Okay, and from here if we want to get the minimum error expectation, then let's continue. Okay. Then from this equation, okay, let's ignore the coefficient 2, then we get this equation. And then we open the brackets, okay, then we will get this is the first term, and this is the second term. Okay, so this is the second term, and this is the first term. And then we move the second term to the right of the equation, it will become this. And here, this is the integer dt, and y of x is irrelevant to t. So we can take y out. It becomes this. And by definition of the marginal probability, okay, so this is the integer of the joint probability respect to t. It is a marginal probability of px. Okay, so we move this px to the other side of the equation. It will become this. And here, what is this? This is the definition of the conditional probability. It will be like this. So this integer, by definition, it is the effect of the conditional distribution of t. Okay. So what does it mean? It means if our error function is a square term, then the minimum of the expected error would be y is the expectation of t. So let's go back to this figure. It means the t is any possible value among those yellow circles. But if the expectation of those t value is exactly this one, then we can get our minimum overall expectation of the loss. Okay, so it looks like this. This is a distribution of t under a given input x0. And we don't care, I should say, no matter what the distribution of the t is, if its expectation or the mean is exactly the y0, then it will have the minimum overall expectation of the loss. Okay. So from another perspective, okay, this is the definition of the expected of the loss. Okay, if we rewrite this is the loss term. If we rewrite the loss term in this way, we minus its expectation and plus its expectation. So okay, and we open the square term. It will be the first term square. Okay, so this is the first term square times the product of the first term and the second term. Okay, so this is the second term, and plus the square of the second term. Okay, so if we do the double integer for this equation, then we will get this one. No, actually, if we only see the central part, okay, and we do this double equation, then we will get the yx minus expectation times the expectation minus t and the double the joint distribution density function. Okay, and because okay, so we can rewrite it as, because this is a double integer dx and dt, and for this part there is no x here because this is a constant. It is, although there is x, so we can move the equation here. And once we open the brackets here, we can divide the first term and the second term. Okay, and because the expression is a number of x not affected by t, so we can move this expectation out of the integer, move it to here. So it becomes this equation. Okay. And by definition of the marginal probability, it becomes this equation. Okay. And finally, what I want to say is, by those definitions, this term is 0. Okay. So what we want to get is the expectation loss. It is the square of the first term. It is the loss. and the double integer of the squared term of the loss. Okay, so here if we use a new symbol, hx is the et expectation, then we will get the expected loss will be the term the yt minus xt and plus the double integer. Okay, so again, if we rewrite it as this term, we will find the central part is also 0. So, okay, here is what the authors want to tell us. It means, okay, the D here is a set of sampled data. So, if we have a set of sampled data, we can create a Y curve. The Y curve looks like this. Okay, so this is the red curve is a Y curve based on a set of observed data. The observed data is the 10 blue points. Okay, so if we use another D means another set of the observed data, then okay, we will generate another Y curve, right? So for different data point, we will have different Y curve. And the overall expectation, okay, is this term. Oh, it means the overall Y expectation minus the hx. What is hx? Hx is the expectation of the t distribution. Okay, so it is called biased square, and here is called variance. It is the Y curve minus the expected the Y curve. So let's recall what is the definition of variance. If we have a distribution, the mean is the weighted average of the variable, and the variance is the second order moment of the variable. It means the variable x minus its mean or its expectation and square the term. So it is exactly the definition of the variance. Okay, so here is what the author want to tell us. It means it is the variance trade-off. Okay, so here, what is the trade-off? The trade-off is the expected the loss. It will be the sum of the two terms. Either it is bias square or the variance. Okay. So let's see this example. If we use a very, very large lambda, okay, then for our polynomial case, okay, then if we use a very, very large lambda and we have 100 data sets, then in every data set we have 25 points, and this what is the curve? This is a curve used the Gaussian kernel regression. So let's show it again. What is the Gaussian kernel regression? Okay. Okay, so this is a example of the Gaussian kernel. Given a training set, and we can generate either this or this or this curve. It depends on the value of C. Okay, so here, let's go back here. if we use a very, very large lambda value, it means we will highly okay. Well, our curve will look like a highly similar to each other. So it means the variance is very, very small. However, the generated result, the hx will be like this red curve. It is will be highly different from the ground truth value. So this is a high bias, low variance case. And if we adjust the lambda value to a smaller one, then here you will see there are a lot of different uh, red curves here. Okay, and they are different to each other. So the variance among them will be relatively large. However, their average, okay, will be similar to the ground truth model, the sign, the green curve. So this is the median bias and the median variance. If we use a very, very small lambda, okay, next one. So the every curve, red curve generated by a set of sampled data will be highly different to each other. So the variance is high, however, the bias is very, very low. So what does this mean? It means if we have a lot of computational load, and if we can sample the ground truth model many times, then because of the bias and the variance trade-off, we can sample a lot of data to generate many different curves. But sum them up to calculate the average. Then we will have a low bias result. Okay. Okay, so here you can see this is a strategy. The assumption is we can sample the ground truth model many times, and we have many computational power to calculate the loss function. Then we can, because there is a bias and the variance trade-off, okay, we can select the model with high variance, low bias, and the overall result will be the low biased output data. It will be highly similar to the ground truth model. Okay, so there is another problem. Another problem. The author of our test further discuss another problem. It is from this table, you see two examples. P is 1 or P is 2. The following questions: do we have other choice? Can we use any other values rather than 1 or 2? And yes, the answer is yes. Our author mentioned equation. It means the robust loss. Okay, so in fact, it's a paper. The paper was published here. Okay. Okay, here. This is a paper. It was published 5 years ago. And what is the paper mentioned something? Okay, so I said the author of the paper proposed a loss function. It is written in this one. There are two parameters. It is alpha and c. And okay, if they wrote the loss function in this, then when alpha is 2, so it becomes what? The L2 loss. It's a range loss or the weight decay. And if the alpha is 1, then it is the L1 loss or the lasso loss. Okay. And if the alpha approaches to 0, then it becomes Cauchy loss. And if the alpha is -2, then it will become another loss called German McClure loss. Okay? If the alpha becomes infinity, then it becomes another loss called Welsh loss. Okay, so this is what you can see it is a generalized term for many different kinds of loss. Okay. And you will see these two figures on our textbook. Okay, so let me. So there are different curves. For alpha equals 2, so it is the term like this, right? And for alpha is equal to 0, so it will be another curve. So it means for every curve you see here, this is a kind of loss decided by the value of alpha. And this is the derivative of the loss function respective to x, okay? Because if we have this definition and its partial derivative would be like this form, okay? So fine. Okay, so so the question is, okay, all right, you have such general loss function. What can it be used? Okay, it can be used to create a probability density function. Okay. Say here, this is a Gaussian loss, right? We are quite familiar with it, and if we use the loss function in the exponential term, okay, and then we can create a probability density function. So here the parameters alpha and c are the same, and we introduce a new parameter mu. Mu usually means the mean of the probability distribution. So here the function, originally it is written in this form, x, a, and c. But here it becomes x minus mu alpha and c, okay? And this is exponential term. And here we have another term called z alpha. It is a normalization term. Why we need a normalization? Because all the integer of a probability density function should be 1, because the sum of all possible cases, their probability should be 1. This is the definition of the probability distribution. Therefore, okay, here we see the alpha equals 0, 1, 2, and infinity. They are certain named probability distribution. And if we draw their result, then you will see this figure. So there's a red, yellow, green, blue, and the purple line here. Okay, so let's write it down. Okay, so I wrote the form of those probability distribution here. So this is Gaussian, and this is Cauchy, and this is student T. Okay, for when alpha is 2, it is a Gaussian distribution. See, and when alpha is 0, it is a Cauchy distribution. Here, that is what we see here. Okay, when alpha is 2, it is a Gaussian distribution. When alpha is 1, it is 0, it is a Cauchy distribution. Okay, so now why I need to mention student T distribution here, because let me show this. Okay, student's T distribution has 3 parameters: mu, lambda, and nu. Okay, when nu approach to infinity, it becomes Gaussian distribution. And when nu is 1, it is the Cauchy distribution. Okay, now Baron proposes his own distribution. There is 3 parameters: mu, alpha, and c. And when alpha is 2, it becomes normal distribution. And when alpha is 0, it becomes Cauchy distribution. So from certain perspective, the student T distribution and the Barrow distribution, they are both generalized distribution of Gaussian and Cauchy. And okay, if so, then the next question is there any point or any advantage the Barrow's distribution is better over the student T distribution? Okay, so in Barrow's paper, he shows some experimental results to to prove there is an advantage. So his experimental result is using a variational autoencoder. The concept of a variational encoder is given let me enlarge it. Given an input data, there are some neural networks, and it will encode the input data in another format. And in this, it is called a latent vector. And the latent vector is in a latent space. And in the latent space, they want those latent vectors follow a certain distribution. And then the autoencoder has an encoder and also a decoder. Okay. From the latent space, if we have any latent feature, using the decoder, we can reconstruct an output vector in the original space. So this is the autoencoder. Okay. And it is called a variational autoencoder because if we can control the distribution of the latent feature, then we can make the autoencoder to do something we want to do. So here is an example. He used the celeb A dataset. And what is celeb A dataset? Here you see a girl here, but if you enlarge this image, you will see there are many faces. Okay, so every faces are from a celebrity. Okay, and the statistics of this celebrity dataset, there are more than 10,000 people, and there are totally 200,000 images. Okay. This is the most important one. So you can see this is a large scale human face dataset. And there are some features, but it's not very important for Barrow's clan. Okay. Then use this dataset. Okay. Barrow created a variational autoencoder. And in the beginning, the input is a face image. So how to convert the face image into a presentation? So there are several different ways. We can, Barrow used the pixels. Pixels means the RGB value. So in the RGB color space. Okay. And so this is the straightforward. It means given the image, it converts the image into a very, very long vector. And the elements in the vectors are the pixels RGB values. So it will become the X of this autoencoder. So this is the X part. And however, there are other representation for the input X. It means DCT plus YUV. So YUV, what is YUV? It is color space. So YUV is a linear transformation of the RGB pixel intensity. And what is DCT? Discrete cosine transform. So when we talk about Fourier transform in previous week, we also slightly mentioned the DCT. Okay. However, you can just imagine it is the real part transformation of the Fourier transform. Okay. So it can convert an image into low frequency and high frequency patterns. There are many given patterns to convert the image into a set of coefficients. So it means, given the image, it first converts this image from RGB space to YUV space and apply the DCT transform on the Y, the U, and the V space. So you can create a vector from an image. Again, this is the wavelet plus the YUV space. And the wavelet, okay, the difference between wavelet and DCT is the pattern or the basis of a DCT transform is fixed. But for wavelet, there are some parameters you can still adjust. Okay, so what the Barrow want to show is given the three different X representation, and here there we want to convert those data representation into a latent space, and the latent space should follow a certain distribution. And here he can control the distribution here. It can be normal, it can be Cauchy, the T distribution, or balance proposed distribution. Okay, and how to measure the quality of a variational autoencoder? The widely used metric is the elbow. The full name is evidence lower bound. It means given two distributions, are they similar to each other? If the two distributions are similar to each other, then the elbow should be higher, and the higher is the better. Okay. So for the autoencoder problem is, how can I design a good distribution in the latent space so that my input can be well transformed to the latent distribution? And here what he shows is using his distribution. Okay, the elbow number is greater than the T distribution, even though the improvement is very, very small. And for the wavelet plus the YUV case, the T distribution is still better than his algorithm. However, they are compatible and similar to each other. It means his proposal is still worthy for some points. Okay. All right. Okay. So we have still another class, and here what I want to mention, we talk about so many mathematical equations, and what is the basic concept? The basic concept is model fitting. What we want to do is to use the observed value to fit our model well. Okay, let's take a break. Okay, so since the title of this topic is data fitting, so here you can think this is the first model, and this is the second model, and this is the third model. Which is the best model for this problem? Of course, it should be either DCT and the YUV space, or the wavelet and the YUV space. The pixel in the RGB space should be the worst model. Okay, so let's see an example of the scattered data interpolation. So this is a colorization task. So why it is the scattered data interpolation? It means, given a grayscale image, if we just set the color of a few pixels, just given the color there, and we want to generate colors for other remaining pixels and generate output. So this is called colorization. And from this image, this is the ground truth image. And how to generate the ground truth image to the input image? In fact, it uses the YUV color space. Okay, so what is the YUV? It is just a linear transformation from the RGB space to another space. So given this image, the RGB 3 channels values look like this. And using this equation, we will generate the Y channel, U channel, and the V channel. In fact, they are grayscale, right? And here, for better illustration, it slightly add the color. Here, this is a pink, pink to blue, and this is yellow to green. Why? Because in the YUV space, this is the converted YUV space. The white point for when R is 255, G and B are 255, the Y is the 155. It will be here. Okay, and when the RG value are 0, then it will be another at the bottom. Then there is a cubic, the skewed cubic in the YUV space. Okay, so this is the colorization problem is an example of scattered data interpret, and how to use optimization to solve the problem. Okay, so this is a very famous paper 20 years ago. It's a very, very old paper. Okay, but so let's see how it do. First, it's suppose the given input is in the color channel of Y, and we want to interpolate those given color. There are triples here. From this given color data, it is the scattered data. We want to interpret the YU values on for other pixels. So, okay, let me explain the notations here. R and S are pixel, just 2 pixels. Okay. And from those given scribbles, we know some UV values. And okay, the remaining U value and the V value the same. They use the same equation to for both U and V. So if we just see the U value, so it defines error function, or you can call it energy function, whatever. It means for a given point R, its U value should be similar to its weighted average of its surrounding S value. So here, S means another pixel at R's neighborhood. Okay, so let's see this example. If I crop this region and then enlarge it here, okay, it will like this. Okay. Say this is the R pixel, and the region is the neighbor of the R. Then for every pixel in this region, okay, the Y value of R should be certain weighted average of the Y value in the neighborhood. And so here the key point is how do we design the weight of the between point R and point S. Okay. The definition is okay. The knowledge we know is only the Y channel, right? Okay, so from the Y channel, we say the weight between 2 pixels R and S, they should have 2 properties. First is, if the Y value is similar to each other, then their weight should be larger. It makes sense, right? It makes sense. For example, the Y value on the hair area is quite similar to each other. So the color on the hair should be similar to each other. And the Y value here is very small. And the skin, on the skin value, the Y value is relatively large. So the color for 2 pixels, one on the hair and another on the skin should be different. should be, therefore their weight should be relatively small. So if their y value, the difference between the y value is large, the weight should be small. It makes sense. Okay. And the second property should be their y value, their normalized y value should be similar to each other. But if let's show it. So suppose this curve, this is the Gaussian distribution, and suppose this is the distribution of the y value in this region. Then, if the y and the of R and the y of S are the same side of distribution, then their weight should be what? Should be larger. Or, and if the y value are on the two opposite sides of this distribution, what does it mean? They are unlike to each other. So their weight should be smaller. So here you can, this is 1 plus a certain product. And the product is what? Mu is the mean. It means the vertical line here. So if the y value and the s value on the same side, either this side or that side, then the term here will be a positive, because positive times positive is still positive. Negative times a negative value is also positive. However, if the y value of r and of s are on the opposite side, then this will be a negative term plus a positive term. So there will be a negative term. And the 1 plus a certain negative term will be a value less than 1. So based on this design, okay, they can create a very, very large matrix. This means for every pixel R, except if they have an image, and there are many, many pixels on the image, but no matter how, you take the pixel and you only consider its surrounding pixels without a given u or v value. So that is what. Let's assume those pixels are variable we want to solve. Okay, say it is x, and there is a match. The y is what? Y is the pixels. Their u value are given. It's like this. For those pixels, their y value are given. So for this, if we want to solve the value of at r, then we only need to consider those pixels in this region. They are the y. Okay, and how? So about the r and the s. Okay, there are some coefficient, and the coefficient is decided by the two weighted function. Therefore, overall, this function will convert it into a matrix minimization function. Make sense? No? Okay, let's say again. So what is x here? The pixels and their u value. And we need to decide their u value. Okay, and what is y here? Y is the pixels. Those values are given. So therefore, like this. If I want to know the value of y at the location of r, I only need to consider its s value. Okay, so those pixels with color, it means the u value are given. Okay, so in this case, it will be my variable x times a certain matrix minus the y is a vector, not just a single value. It's a vector. It means all given value of the U channel for those pixels we know. Okay, and the x is also a vector, and the x0, x1, x2 is the u value of those points. Okay. Therefore, this is a linear equation problem, and it can be solved by certain numerical analysis tool like MATLAB. And then there are some more professional software program which is designed for solve this problem. And what we want to get is x. Okay. So the concept is not difficult. The concept is easy. And let's see the result. So given this input value image, and there are many scribbles assigned the lake of the water, the grasses, and the rock. And here there are two cases, and we need to assign the cut. So for this algorithm or this method, you need to create a sufficient scribbles so that you can generate a good colorization result. And the author also show the interactive colorization. It means given this input image and some scribbles, okay, it will generate this result. But when you find some artifact here, for example, close to the nipple, close to the pacifier area, because the pacifier is green, so the background region become green purple, green blue, etc. Because their y values are similar to each other. And for this table, because the author didn't assign any value on this table, so it becomes the color of the clothing, right? So how to solve the problem? The author add some more scribbles here and here. Then it can adjust the color generated. And again, if he want to add some more, assign some more colors, then it can add some more scribble here, here, and here. Then it can generate a new result. However, you can still find artifacts here. Let's enlarge it. So here, this is the table, and this should be a straight line, right? But because the y channel, the y value on the table is very close to the clothing, so the pink color of the clothing, it go to the area of the table. And let's see, this is the application of the colorization by optimization. It means recolor. It's given an image, and the author can select a region he or she want to change the color, and keep the remaining regions the same, and add some scribbles here, so the color from orange become green. And for this example, the white region is where the color won't be changed, and he add some scribbles on those yellow region, and it can change to another set, the purple. So here, let's see another example. This means a video colorization. So this is like a video clip. There are 83 frames, and in the 7 frames, the author add some scribbles there and use the scribbles to generate the result. Okay, here let's explain something. For video, how do you let's say here on an image, this is the neighborhood region, right? Okay, so it for R, there is a neighborhood region. And for a video, we still can define the neighborhood regions. If you think the video is a friend and a friend and a friend and a friend. So for a single friend, the region is the neighborhood given a pixel R. The neighborhood region is also a two-dimensional plan. But for a video, you can imagine it is a three-dimensional data. So given a point, you can design a region, okay, including a few friends beforehand and a few friends in the after. That's the reason he created the video correlation. Okay, so there is an interesting question. This paper was published 20 years ago, and then is there any new paper similar to it but relatively new? Usually, new paper has the new contribution and new yes. So I should say this paper is mentioned by our textbook's author. Okay, it was published in 7 years ago. Okay, so see, given an input image, what is the author? This method don't need a lot of strip. It just need a few points, and just give a few points is color. So it based on those few points, it is partial of those point set. It can generate this result, or this result, or this result. It depends on only a few points. So how do this do? Okay, so let's do some superficial comparison. So Levine's paper, okay, it doesn't use neural network, but Zhang's paper uses neural network. Okay, and because it uses neural network, it requires training data. So how many data does it use? It uses 1.3 million images from ImageNet dataset. It's a quite large size. And because Zhang used the neural network, it can generate the results in the real time. So it is a quite good advantage. Right? But Levine's paper cannot. And is there an automatic mode? What does it mean, automatic mode? Automatic mode, given an input image, you don't need any, okay, you don't need any color point. Then you can still generate results. So this is called automatic mode. This is okay, but however, for Levine's method, you must provide the scribbles. So there's no automatic mode. Okay, and okay, performance is higher. So let's see its performance later. Okay. So this is the figure 6 in Zhang's paper. So Zhang's method is this. Ours here it is this line, and okay, the x-axis is the number of points. So it can give only a few points and give a lot of points. And the y-axis means the PSNR. PSNR usually is a metric compare the similarity between two images. The higher the better. And Levine's paper is this one, the brown circle. So it is this one. Okay, so it shows what? When you only offer a few points as the reference data, then Zhang's paper performs better than Levine's paper. However, if you offer more reference point, the performance of Levine's paper will close to will converge as Zhang's paper. Okay, and this is some qualitative comparison. Okay, given this grayscale image, suppose we only have a single reference point here, then okay, based on Levine's paper, because they have single point, so the color in this image are almost the same, right? Okay, because they are single input. But however, because John's paper is trained from a lot of images in the ImageNet dataset, so based on a region, okay. Oh, sorry. Cannot. Okay. Based on a region, okay, it will compare. I should say, the neural network remember where he saw this patch in the image data set, and if there are some similar slice of grape orange here, then it will remember. Oh, okay. The color of this region it should follow certain distribution, so it will reconstruct the color. So that's the reason when we see other pixels, if there are more pixels reference point, it will generate result of this. And the last one is the ground truth image. Okay, because there is a ground truth image, they can calculate the PSNR value. Because if you want to calculate PSNR, you need a reference image and your generate the image. And the reference image here is the ground truth image, right? Okay. And let's see their automatic mode. I should clarify it. When you see this paper, it was published in TOG 2017. And the TOG means transaction of graphics. But a few months ago, John published another paper in ECCV. So, in fact, John did his work for the ECC paper first, then extend the ECC paper and submit it to TOG and accepted. So what is the work John did for his ECC paper? In fact, it is a fully automatic colorization algorithm. So let's see some results here. It means given a grayscale image without any reference point, no scribble, no any hint, their algorithm aims to generate the color channels of this image, and this is the good result. So how do they do? Okay, let's see. This means given an input image, and they developed a neural network. We will talk about neural network next month. Okay, and given the neural network, there are many parameters in this neural network, and they will learn the training data. Okay, so this means suppose there are some training images, it is also a butterfly in the network. So then, given the training image, it will, here, I want to mention, John used LAB color space rather than the YUV color space we see before. Why do they choose LAB color space? The reason is very straightforward, because LAB color space is the intuitive color space. Remember it? It means the Y is brightness, and the AB channel means the chromatic channel, and the distance in the LAB color for 2 points in the LAB color space, if their distance are similar to another 2 sets, so human perceptions, their change or their difference are the same. So they use LAB color space, and given a training input, they will generate a grayscale input. So it is the first layer of the neural network. Then through their neural network, they will generate a predicted LAB color space. So they can easily compare whether the generated AB channel values are similar to the ground truth AB channels. So when the neural network sees there are totally how many images in a okay. There are totally 1.3 million images. A lot of images. Okay, then the neural networks learn. Okay, when it sees certain pattern on the image, this if he saw a certain pattern here, okay, it should not be so small. Sorry, I should enlarge it. Okay, because the size is 255 times 255. If he saw certain pattern in the input 255 to 255 region, then it will generate reconstruct its AB channel. So this is okay, their approach. And then after learning the network parameters from the 1.3 millions, so they can, okay, when they saw such a pattern, okay, they will thought, it should be a red ball or something. And then when they saw this pattern, or they will see, okay, this is a human hand. And so the color of the human hand should be somewhere like this. And then when they saw this pattern, they will say, okay, this is a mountain top, and the color should be white, and the surrounding color should be blue. So this is what neural can learn the proper parameters or the weight inside. Okay, so then how to evaluate the performance of the neural network? They use this approach. They hire a lot of Amazon Mechanical Turk. Okay, so it means given a ground truth image, and let me enlarge it. Given a ground truth image, they will generate the grayscale channel, and they will use their method to create a color image, and then they ask the Emerald Mechanical Turk, is this a true image or a generated image? Okay, and they get, for some images, they get this result. 28% of the Emerald Mechanical Turk say this is a true or ground truth image or true image. So because it looks like real, but for some other region, for this one, this is a ground truth image. This is a, sorry, you didn't see the laser point. For this is a ground truth image, but this is a generated image. It doesn't. Okay. Oh, sorry, I cannot. Okay, it doesn't look like a real. So on 0% of the mechanical Turkers feel this is a ground truth. So it means some image they get good results for certain image, but a poor result for other images. Okay, so their algorithm, the performance of that algorithm really depends on the category of the image or the image itself. Okay, why it happened? Because in the network, if the network saw sufficient similar training image, okay, then the probability to generate a realistic output image is high. Otherwise, the probability is low. Okay, so here, this is the John's TOG paper. Okay, this is RT architecture, and in this part, this okay, this is the automatic part. It was created for its 2016 ECCV paper, and he extend this part, okay, and this part for its 2017 TOG paper, because this is the local hint. Local hint is the point used here. Okay. So this is a local hint point. Therefore, it can compare his TOG paper with the fins, because in his ECCP 16 paper, there is no input local hint, so there is no hair-to-hair comparison. But in his 2017 TOG paper, since there are local hints, so they can compare with each other. Okay, now that is example. Coloration is the example of scattered data interpret. Now we are going to the lesser chapter of the lesser section of the our chapter 4. It's called the Markov random field. It is an optimization problem. So let's recall. The title of this chapter is Model Fitting and Optimization, and use some optimization approach, we can solve some computer vision problem. And let's explain what is the Markov random field. It means if we want to figure out the data of f, okay, but we only have some observation or input data, it's called D, okay, we can create a certain relationship. It means the C between the input data and our variant f. And in addition to D and F, there are other terms of the cost. Sometimes some people call it cost, some people call it energy. It means for two adjacent pixels, they have a certain relationship. It is described in this S, and the S can be any arbitrary relationship. And there are also, so it means, I should say, usually there is two types of neighborhoods. One is 4 pixels as your neighborhood, so it will only be the SX. It means x-axis along axis and along y-axis. For this example, its 4-point neighborhood will be this one, and this one, and this one. And for its 8-point neighborhood, another model, it will be 1, 2, 3, 4, 5, 6, 7, 8. So therefore, you see the blue lines and the blue rectangle here means for the 8th pixel neighborhood. And the Markov random field, in fact, what it is another format of the Bayesian rule. The Bayesian rule means if the x is the f, the variable we want to know, but we only observe the y. Y means our observed value. So if we have certain probability model, we know the probability of the x itself and the conditional probability of the y under x. Then we can get its probability of x under y. Given our observation, we want to know its variable x. Okay. So the model itself is, I should say, straightforward，那就是 clear. Okay, by the definition. And let's see its application. It's called interactive segmentation. So there are two examples. First, it means given a grayscale image, and let's given some scribbles to define which scribbles is the foreground. Foreground usually means the object. So the red scribbles means those pixels belong to the object. And the blue scribbles means those pixels belong to the background. And we want to segment the object from the background. So it is called the segmentation problem. So this is another example. And in addition to scribble, there's another algorithm called, this. It means given a rectangle, you use the rectangle to enclose your foreground object. Then the algorithm will automatically segment the foreground object. So there is no scribble. You just need to input a scribble. So this is another example. So from the grab cart algorithm, it has a name called grab cart. Okay, and in its paper it shows, I should say, this paper grab cart. Was also a very old paper. It was published in 2004. Now it's 20 years ago. Okay, and this year there are some existing segmentation algorithms. So the magic wand is give some scribbles, and you will generate this result. And the intelligent scissors will be, you will click on many points, and along those points it will cut the image out, the object out. And there's also alpha mating approach, and the knockout is an algorithm, private algorithm or proprietary algorithm. It is a plug-in for Adobe Adobe Photoshop, but developed by the Corel Corporation. Okay, and the grab a cart. Okay, so this algorithm is called grab cart. Okay, and graph cart, and the authors proposed is graph cart algorithm. So what is the relationship between the graph cart and the grab cart algorithm to the Markov random field? Okay, the reason is in the grab cart algorithm, it is proposed by Boykov in 2001. Okay, it models the segmentation problem as a Markov random field. So it's like this. This is a very small example. There are only 9 pixels. So it assigns this top left corner is the background, and the right bottom corner is the object or the foreground. Then it creates a Markov random field. For every 2 adjacent pixels, it will define the smoothness term. The smoothness term is defined as this. So from this equation, you can see what it is. If the intensity or the brightness of the 2 pixels, PQ and the P and Q, are similar to each other, then the cost you set a cut between the pixels is high. Does it make sense? Let's go back to this. For example, from this image, where do you think you will set a segmentation? Along the edge, right? So why don't you set a segmentation between these 2 edges? Because their intensity are similar to each other, right? So therefore, this is a smoothness term. It means if the intensity of 2 pixels are similar to each other, the cost you set a cut or a segmentation between them should be high. So if their intensity, the difference between their intensities is large, then the cost should be smaller. Okay, so, and another is the pixel label. It means, let's go back to the bank of random field. Okay, so for every variable, you have some observed value and your lead variable you want to solve. And in this model, the variable you want to know is the label. It can be either object or foreground or background. Okay, and the intensity in this patch is the observed value. It is the D value here. So based on the D value, you want to know whether the F, it is the foreground or background. So this becomes the Markov random field model. Okay, and okay, so it is modeled like this. The RA is the probability of the I is okay. The cost is the probability of the intensity under a distribution, and the distribution. What is the distribution for the local region? Okay, there are many pixels, and the layer intensity will form a histogram, and from the histogram you can calculate the probability of the intensity value. So what does this mean? It means if the pixel here is very similar to its surrounding pixel, then the cost you cut here from this pixel to as an edge should be high because the probability is high. It is similar to its surrounding pixel. Okay. However, for this surrounding pixel, the suppose there is a histogram. Well, I should say, okay, this example is too small to show it. Okay, so what do I want to say? This paper is published in 2001, and 5 years later, the same first author, Boykov, it proposed another method. Okay, you still use the Markov random field, and the difference is in its 2001 paper, there is no direction. It means the cost from P to Q and from Q to P is the same. But in his 2006 paper, it used a directional graph. It means the cost from P to Q and from Q to P will become different. So this is the medical image. It's called, so you can see liver here. From using the new application, it creates a better segmentation result. Okay, so let's go to the graph card. This is the paper published in 2006. Okay, the graph card, let's say, given a rectangle. What does the rectangle mean? The rectangle means for pixels outside of the rectangle, all of them are background pixels. So this is information given by the. Okay, so from the background, it can do a first automatic segmentation and generate the result like this one. But for the helmet, because the color of the helmet is very similar to the rock at the background, so it will think, okay, this is the background. And for the shoe here, because the shoe is very similar to some shadow, so you do not see the show in the automatic generator. So it will use some user interaction. The white scribble means this is a foreground, and the red point means it is a background, means remove it. Then with the interaction, you will generate better segmentation like this. Okay, and the major difference of the graph card and the graph card is, okay, first, graph card use the mixture of Gaussian model to model each color distribution in RGB space. So this is an example of Gaussian mix of Gaussian. So there are three Gaussian distribution and mix them with each other. And if we draw it another way, it will look at first, third, and second Gaussian, and it will generate. So this is 3D illustration. We have seen an example of the mix of Gaussian distribution. It is this, the old face. Remember this? So this is also a mixture of Gaussian distribution, and there are two Gaussian distribution in this case. Okay. So for the graph car, it would generate a result. Okay. So there are a few approaches, and it is slightly complicated. However, it is a iteratively converge. So this is an optimization problem. Okay. So I should say, let me show. There is also car. So there is also design and energy. So this is also a Markov model under Markov random field. And it has iteratively updated its parameters of the mix of Gaussian Gaussian mix model. So this example is, in the beginning, okay, the red and blue regions means the Gaussian of those color pixels. In the beginning, they are highly overlapped to each other. The reason is, okay, when you give a rectangle, you will include some background image as the foreground. But however, with several iterations, you will separate the two distributions. So, okay, and the energy will gradually reduced. And then they also offer some technique called border mating. It's a type of alpha mating, and it will generate a smooth boundary. That's what they want. Well, let's see some result. So there is no interaction. They generate. So for the border, it looks good because of the border mating. And here for this given image, they will design certain regions to do alpha mating. Okay, so you can see the fur. It looks quite good. And for this butterfly, it will assign. Okay, so there's a human interaction. This is foreground, and this is background, and this is a region for alpha mating. So it will look like generate a result like this, and the result looks like quite good. So in your textbook, you will see this method, graph card. Okay, so see, and what there, I should say, that is an example or an application for Markov random field. And what is Markov random field? It is a model using optimization. Okay, so that's the reason this chapter is model fitting and optimization, right? Okay, so that's all of our course today. Do you have any questions? Okay, no, if so, thank you very much. See you next week.